This is joint work with my most recent PhD graduate, Todd Hester, and this actually is the journal article that contains the main contributions of his PhD thesis. Todd is now, was hired by Nest, the company that does smart thermostats or home automation, largely on the strength of them finding a direct application for the algorithm TEXPLORE in their industry, or in their problems. So this is in the context of our motivation here is robot learning. And I'm not going to dwell on why we would want robots to learn. And it's also in the context of reinforcement learning. And the talks prior to this gave a great motivation for that. The idea is that we'd like reinforcement learning to be able to be useful on robots. But there are challenges, and mainly it's that many reinforcement learning algorithms take a lot of experience. And robots, if you take a lot of experience on them, they break before they've learned. And so the existing model-free methods can learn a value function directly from interaction. They can run in real time, but they're not very sample efficient. They take a lot of experience to learn. Model-based methods tend to can mitigate that. They learn a model of the transition and reward dynamics. Then they update the value function using that model, which is sort of the reinforcement learning use of the term planning, which is not the full planning that's in the context of this conference usually. But then they can update these action values without taking real actions in the world. The problem is that model-based methods often are computationally expensive. And on a robot, sometimes you'd like to be able to do the learning and the learning and planning while the robot is continually acting. So our motivating problem or domain for this research was velocity control on an autonomous vehicle. So we have a real autonomous vehicle. We upgraded it to have shift-by-wire steering and brake actuators, and it's trying to act. We treated it as having 10-second episodes, and it's acting 20 times a second. And we want it to be able to keep doing that acting while it's doing the learning. And so this is what motivates the computational complexity. So just little details about the task we're looking at that's used as the main test bed in this paper. The state is the car's current velocity, its desired velocity, so it's a velocity target kind of task. You could do this with a PID controller. We're trying to do it with learning. You have the current accelerator and brake pedal positions. So that's the sort of four-dimensional state. The actions are you can either do nothing or you can increase or decrease the brake position or the accelerator. So there's 5 different possible actions. And then your reward is just for each of those 20 time slices per second, how far are you from your desired velocity? And so just to show, this is the car as it's actually doing the learning. It doesn't know anything. So in principle, you can think it doesn't know anything about what the accelerator and the brakes do at first. It needs to actually experiment with them to be able to figure out what they do, build a model of what they do, and then figure out how to maintain the desired speed. And it did this broken into 10-second episodes. So the desiderata for the algorithm, for the TEXPLORE algorithm, are that the learning must learn in very few actions. It has to be sample efficient enough to run on a real robot. It has to take those actions continually in real time while learning. That's the computational complexity. And then for any robot problem, you have to be able to handle continuous state and deal with delayed actions, because you can decide to press the accelerator and it takes not just a 20th of a second, but there may be some delay before the action actually takes effect. Notice that one of the desiderata here is not to find the optimal policy. Okay, we're going to have to give it, to be able to meet all of these constraints, we're not going to be able to give you a guarantee that we're solving building the correct MDP and solving it optimally. This is just a picture of our actual, this was a prototype autonomous car, so we actually had wires that were doing the braking, and this is why you have the actuator delays. So in the journal article, we compare against several other reinforcement learning methods and break them down according to whether they have those 4 desiderata, and found that none of them, there's algorithms that can do each of those, or even in some combination, the sample efficient, real-time continuous, and actuator delays, but no algorithm that could handle all of them easily or be easily adapted to handle all of them. And so that's what the TEXPLORE algorithm does. One of the things we did is we created a robot operating system, ROS package, that is publicly available. So if you are interested in playing with the TEXPLORE algorithm, you can download it and use it on your robot. So I'm just going to, this is a short talk, I'm going to just briefly give you a sense of how we addressed each of these four challenges or desiderata for the algorithm. So first, for sample efficiency, we're treating the model learning as a supervised learning problem. So where we have states and actions, and we're trying to learn a distribution over next states and rewards. We do this by treating them, having a factored model that's learning a separate model to predict each next state feature and reward. So given the current state, given the action you take, how is each feature going to change? And it's a separate model for each of those. What's the one-step reward going to be? It's a separate model for that. And we do that using decision trees. And the thing that's allowing us sample efficiency is that we handle the exploitation trade-off by actually building a random forest of these decision trees, where each one is taking some subset of the past experience the robot has seen and building a predictive model based on that subset of experience. And so this gives us sort of a distribution over possible dynamics. Each tree represents one hypothesis of the true dynamics of the domain. And then we take the decision forest, each predicting some different reward and some different next value of the state feature, and plan in the average model. So basically average the outputs of the decision forest. And what this ends up doing is, in practice, what we find is that it limits the agent's exploration to state actions that appear promising, while avoiding those that based on the model are predicted to have negative outcomes. So it is fundamentally planning to explore, finding a state that it hasn't been in, and planning a path to get there to experience that state if the decision forest is saying there's no harmful effects, that we're not predicting any harmful effects there, and there is some probability that when you explore there, you will see positive rewards. And then on the flip side, basically, I mean, I think one of the key insights in this algorithm is that it actively decides some parts of the state space never to explore because of the predicted, based on the current model, predicted negative outcomes. This is where we lose the optimality. It could, because there's places it's never exploring, it's possible that in those places there are positive rewards. So that's just in a minute. There's a lot more details in the article, of course, about this our method for building up the decision forest for to balance exploration and exploitation. The real-time action selection is achieved by a general, actually this could be applied with any reinforcement learning algorithm, a general real-time action selection architecture. So this is a picture of the traditional view of what a model-based planner or model-based reinforcement learning algorithm would do. You take some state and reward, you store that, and then update the model based on the new state and the new effects of your action. Then once you have your updated model, you could plan on that model and then return the action from the solved MDP. The problem here for our purposes is that the model update can take too long and the planning can take too long. And so in response, we built a real-time model-based architecture that breaks those three steps into three separate parallel running threads. So there's an action thread that at the action rate of the robot, so in our case 20 hertz, is just picking the action that is currently returned by the planner. In the background, as you get your new state action, next state reward tuple, you put that in the model learning thread that can then build the next decision forest. Meanwhile, the planning thread is planning forward from the current state, and when it's time for an action, it returns the action that is best. And there's a series of mutex locks here so that there's no data race conditions. And so we end up with basically a sample-based planning. Embedded in here is basically a UCT Monte Carlo tree search planning algorithm like we saw in the previous talks. And I'll comment on the discussion that was had there. We found that actually we use a parameter to balance between the one-step, basically updating based on the one-step model versus the rollout. And we did find that intermediate values of that parameter performed better in practice, but also biasing towards the one-step, as you were commenting. With regards to the continuous state, rather than just using decision trees with discrete outputs, we use standard. This is not a particular innovation. We just use standard regression trees to model the continuous state, M5 decision tree regression trees. So we end up discretizing the state space for the value updates from UCT, but then we still plan over the continuously valued states. And then finally, to handle actuator delays, that basically turns the problem not into a Markov problem, but into a K-Markov problem. And so if we provide the model with the previous K actions, similar to what the U-tree algorithm does, and then the trees in the decision forest can learn which delayed actions are relevant. And so it actually can say that maybe the actions are the result of the action, or the effects are the result of the action you took 5 steps in the past, and ignore the past 3 or 4. That's something that's learned based on experience. And then UCT can plan over this augmented state action histories. We did, as I said, we ran this on our autonomous vehicle using ROS, using a ROS implementation, which is basically a way of providing the same functionality, if you're familiar with RL Glue, basically an interface between the algorithm and the environment. And then in the article, I don't have time to go through all of the experiments that we did, but we ran simulation experiments against several different simulations on this autonomous driving task. So using a simulator of our car against many different approaches for exploration, different sample-efficient methods, continuous models, real-time architectures, and methods for dealing with actuator delay. We sort of isolated each of these, and there's sort of happy graphs in that show that TEXPLORE does comparable, or comparing to the sort of the best state-of-the-art algorithms along each of these features. I'm not going to dwell on them just due to time constraints, but they're all in there. They're also, I should say, these were all of these, we did it all on a simulated car control task. Also, for each of these, there are some experiments on other domains as well that have been used. So there's sort of this common thread of the simulated car control, but then for each of those different challenges, we look at sort of appropriate domains. For continuous state, we have a continuous, like the traditional mountain car task and things like that. But the main goal, like I said, was to make this work on the physical vehicle. And this is showing that in 2 minutes of driving time, so I showed you that what it looked like when the car was learning. Over just about 10 episodes, it was able to get basically to get very close to the target speed, all with all the learning happening in real time. So this is 2 minutes of driving and 2 minutes of computation. It was able to, and we have graphs in the paper also showing it was basically able to do as well as a finely tuned PID controller, but without initially knowing what the brakes and actuator do. It had to plan to learn a model of those as it was going. And so that's the overview. Due to the short talk, I had to skim through the results, but I can go back and talk about any of them if you're interested. The main thing I'm trying to, trying to use this to motivate you to look into the TEXPLORE algorithm, especially if you have some task like robot learning, or like Todd is using at Nest, where they have to learn thermostat control, where you have few samples compared relative to the size of your state space. You want the learning to happen in real time without sort of an offline period for the computation, where you have continuous domains and you can handle actuator delays, but you're willing to give up on a proof of optimality in the end. And all of Todd actually created some really nice, an annotated slide deck from his thesis that's available online that goes into a lot more detail, and the source code is available as a ROS package. So with that, thanks for your attention. I'll be happy to take questions. Ronan.
So you didn't have time to go into it, but can you explain how you start the, you have to start with some reasonable model to learn so quickly, don't you?
So in some of the domains, actually on the simulated car task, we didn't have any model at all to begin with. So it really is just taking random action, press the accelerator. It can notice after doing that a couple times that when you press the accelerator, you tend to change your velocity in a positive direction. It's learning relative transitions.
So in 10 episodes, it was able to learn, and each episode is how long? I mean,
10 seconds, which is at 20 hertz. Okay. So it's
200.
Right.
Okay. 200
actions, but right. So it's learning now. Okay, but in some of the domains, in sort of domains with larger state spaces, we didn't seed a model. We seeded a couple of experiences. So we gave, so if we needed to bootstrap it or get it off the ground, we'd say, here's a single transition to the goal, for instance. And then that would provide enough of a model for it to, there's aggressive generalization in the model learning.
Right.
And so that would give it enough of a impetus to plan to see states in that general vicinity.
So continuing with that, could you envision reasonable cases where, because of the aggressive learning that you mentioned, you would actually be doing something wrong? Or
yes.
Would that be improved over time anyway?
Yeah. So well, first of all, yes. Like I say, we're not proving optimality, so we can certainly be. What the algorithm is likely is it's quite possible that it could be missing opportunities. By not exploring a place where there would be really positive rewards. What it won't do is repeat mistakes. Okay. So it will learn that if it's doing something and getting negative rewards, that will become a part of the model quickly. Okay. So the thing that the aggressive generalization does is basically cut out, and I use the example that, we do this all the time, right? I mean, there's a building outside of my office that I can see and I've been able to see for years, and I've never walked into that building because I have a model that exploring that building is not going to add anything to the quality of my life. But it's possible I could go in there and my own personal nirvana is on the second floor or something, right? Right, so the philosophy behind this is that, for a robot to learn, just like us, it has a limited lifetime. It can't explain, the world is too big for it to explore everything. You just want to avoid the mistakes. Malik.
I missed how you estimate the key value of your key Markov process. And is it uniform for all your state variables, or is it variable?
No, so it is uniform, and we just give that's basically a user input, but we give an upper bound. So the nice thing about it, and this is something we emphasize in the paper, is it's not important that we get the right k. It's just that we get a larger k than is the true delay, because it'll learn what value is important. So there are some of the competing models require that you actually do get the right amount of the right k. Right, but we can just give an upper bound. As long as we're overestimating, then the decision tree learning will focus in on the correct value. So because of that, we also just simplify it and say it's just a single parameter for all of the different dimensions.
One quick question, Sean.
So just a quick question for this particular application, but maybe others. It looks like the difference between the target and the existing velocity would be just one criteria, and you would want to guarantee other things like fuel economy, comfort, and so on. How would you would feel that this would extend to multi-objective situation?
Yeah, I mean, the first approach to a multi-objective situation is to collapse them all into a single reward, and if you do that, then the algorithm works unchanged. I mean, beyond that, I think the work on multi-objective that looks at Pareto frontiers and things like that. I think there's no reason. I mean, this is the. I don't think there's anything that makes this particularly more or less applicable than other sort of underlying reinforcement learning approaches for multi-objective optimization. It's not something we've focused on in this work, though.
Since we started late, let's take questions offline. Let's take Peter again.